machine tools and machining. So let me go over this. We are going to solve some problems today. Machining economics. This is the topic which we are covering today. Okay. And I went over this. This is the structure of Japanese manufacturing cost structure, which tells you that the material cost is very high. About 50% is the cost incurred to material, to purchasing material to make products. So the profit is 10%. This is just a percentage, but when you go to actually, it varies a little bit, plus minus. Then the cost is of different types. Fixed cost, like the cost of machine, if you want to purchase, it has a fixed cost, and the direct cost and indirect cost. So the land cost can be assumed as the fixed cost, direct cost, the machinery cost, and the labor cost. Indirect cost could be the taxes, insurance, other than the uh, retail price. We have to pay more than that, like you see over here. If you want to do some math to start a company, manufacturing company, you need to do some math. What is the cost, fixed cost, the machine tool purchase, the life of machine in years, and the book value. Book value is the cost plus it could be the maintenance cost included, and you see it has some taxes or interest rate included. So this is the fixed cost per year. The same formula can be written in another way, that an average cost, this was the this is the average cost, whereas TA is the taxes, average annual taxes and insurance rate. So the direct cost, it comes from material, labor, power, setup. I would suggest you reread these slides at home because I want to do some problems. And indirect cost includes some the building cost, taxes, insurance, heat, light, ventilation, power, energy, and the machine maintenance, material handling, engineering, inspection, office help, administration. Even if you hire somebody, you have to provide him office space, you have to provide him some laptop, and provide him some insurance for the workers, company's responsibility, and some retirement plan. If you are making a nice company, provide some retirement and give some incentives. So these allowances are all indirect costs, which are the burden, overhead burden. We call, you will see a word which burden. B stands for burden. So suppose if the basic labor cost is suppose $10 an hour, and the labor cost also, you have to add maybe 15%. This 15% comes from the burden to provide insurance, to provide incentives, to provide office space, laptops. All these are the burden on the employer to provide, other than the basic cost. So the total cost will be the including the burden. So I'm going to show you in a bit. You see over here. So the burden comes from overhead, which you have to pay out of your revenues to help your workers. Okay, like health insurance. Some companies, they give health insurance benefits. This is the overhead burden. It is not directly related to the production of the number of parts. You see, all this cost, hourly cost, can be calculated the total number of cost. C naught divided by number of hours per year, including the depreciation, the taxes, the insurance, the maintenance, and uh, labor, and plus the overhead burden. You see, this is all hourly machine cost. And we will go over these formulae. The cost to produce one piece. Suppose one part you want to produce. How many types of costs are machining cost, idle cost, setup cost, tool changing cost, tool grinding cost, raw material cost. So there are six types of costs which you have to pay in order to produce the part. You see, the when I went over the machine shop, he was using some tool changing methodologies to change the set up the tool, to change the tool, to grind the tool. These require the labor work, so you have to pay for these types of cost as well. Okay, suppose if I say machining cost, so machining time per piece. Okay, time, the labor rate. RM stands for the labor rate in terms of the fully burdened labor rate. This is one of the example to find out the machining cost. Suppose it takes about 5 minutes, and the labor rate, including the burden, is about $10 an hour. So you will convert minutes to hours to find out the machining cost. Do you understand that? So you will similarly you will find out the idle cost. If the machine is not running, you are still paying the cost even if it is not running. Idle time per piece times the labor rate. Labor is there, workers are there, although the machine is not running. You see my point? So you have to pay off this cost, tool setup cost, or the machine setup cost, setup time times the labor rate. I would say RS. RS means setting up the time. The when you say R, it includes the burden, overhead burden, plus the direct labor. Suppose $10 an hour, you also pay overhead burden divided by number of parts made per setup. If you set up one tool, for suppose the cutting tool, which is turning tool, and you make three parts, so you are paying that much cost, number of parts. This is number of parts in one setup. Then you have another tool, another setup, you pay another. So you see, so tool setup, the machine setup cost, and tool changing cost. What is tool changing cost? Let me show you. Cost to require to change the tool is the tool changing time. Small t is the time. Okay, this is the time required to change the tool. And who is changing? The workers, the labor, they are changing the tool. And time, machining time per piece divided by the tool life. Suppose tool life is 10 minutes and machining time is 2 minutes. So one half. So you can use that tool 5 times. You see my point? So another cost is tool grinding cost. You can use the tool grinding cost. This formula you can use tool regrinding time times the labor rate, including the burden. Okay, this is the times the cost per tool edge. There might be some edge like diamond shaped tool bit, like it has four edges, one, two, three, four. Sometimes on the other side it has further four edges, but you have to See, you will see similar problems that there are four edges on one tool bit. Then you have to grind them, okay? And then TM over T. What is TM? Machining time per piece, and the big T is the tool life. Yes. I'm sorry. This is a plus sign. This is a plus sign. Thank you. So cost per tool edge grinding. Okay. So and then we come to the raw material cost. And what is the raw material cost? Let me show you. The raw material cost includes the part weight, part weight plus the scrap weight, 1 minus salvage value times the cost per weight. WT stands, for example, 1 pound steel, how much material you have to pay. Part weight plus the scrap weight, 1 minus the salvage value. Because salvage value is the value is still possesses salvage value. If you go to the junkyard for recycling, you get that money back. So that's why we have to subtract that salvage value. Six costs. Okay, so let me show you. Let me show you these six costs. Total cost to manufacture the part, it includes six different costs. Have you understood these six different costs? Type of safety. That's good. If you have understood, that's good. Then comes some description about the formula for the machining time. Time, machine the part. Suppose in turning, axial length divided by feed rate divided by N. I'm sorry, this is N. Axial time is second. Sorry, this is in meters. This is axial length. Suppose it's a turning. This is very bad picture. But if you, so what is the axial length? This is my axial length. You want to turn this down to this much length divided by the feed rate. Suppose inches divided by inches per minute, and the speed inches per second. This is the speed. And the Taylor's tool life is represented by this formula. This is a very important formula, that the speed times the time. Tool life. This is the tool life. Cutting velocity. I want to show you some algebra which tells some calculus. Suppose if you want to optimize between the cutting velocity for minimum cost, CM stands for minimum cost. Okay, if everybody wants to reduce the cost of manufacturing. So what should be the speed of the tool? Okay, and what is the tool life for minimum cost? So minimum cost cm. So let me tell you. So let me show you. There are two types of, okay, over here. Suppose if you have cost on the y axis, and on the x axis you have the speed of the tool. So as the speed increases, this is the machining. Machining cost reduces as you increase the speed. In suppose lathe machine, if your speed is very fast, but you know what happening on the other side? This is the tool cost increases, okay? Because you are changing as the speed increases, the tool cost increases as well. And similarly, tool changing cost will also increase. But the raw material is the fixed cost. Similarly, material handling, conveyor belt, or some pallet racking, you have to pay some uh, fixed cost for that. So let me show you. The total cost is this one. Let me show you a graph here for this machining time. You see, optimization means you are trying to save money by increasing the speed of the cutting speed of the tool, and you also saving the money to increase the tool life. And on the other hand, you can increase the production TM, maximum production. What is the cutting velocity? So I will show you two formulae. Yes, the cost. Let me show you over here this graph. So the cost increases when you are using, like, you see the speed is increasing, so you will change one tool here, second tool, third tool. How many tools you are changing? Like one time you one edge is ruined, then you will put another tool. You are tool changing cost also increasing, because if you are doing the operation in the lower speed value, you don't have to change the tool, you don't have to replace the tool bit, because the speed is very small. But when you want to maximize the production, because you are paying the labor, you ask him to increase the speed of the cutting speed, then you are working in this range. In this range, tool life is reduced, therefore you have to keep replacing the tool. Now we have to do some calculus. You remember maximizing a function with respect to double derivative. If you remember that calculus class, right? So you get this formula. Please write down this formula in your notebook. This is, if I ask you, what is the cutting speed to reduce the cost, to save the money, you will use this formula. And if I ask you, what is the minimum cost of the tool when you produce a lot of parts but at the minimum cost? So these are the two formula after optimization. You don't need to derive it, you just write it down, but I have given you the definition of each cost. Six costs, right? Six different costs. But after doing some calculus, you find out this is the speed to reduce the cost, the speed required to reduce the cost to a certain level. And the tool life, and what is the tool life? If you have maximum saving, this is the formula. But on the other hand, if you have maximum production, what is TM? Okay, what is VTM? What is tool life for maximum production per hour? So you will use a different formula. So let me show you. This is the time formula, and this is how. So you will use these two formula. So there are two different formulae in optimization. One is to produce this PD, you will use this formula for maximum productivity, maximum production per hour. And you will use the tool life for maximum production per hour. Do you understand this form? Let's apply this formula into a problem. Okay. Okay, let's do this problem. For the following cut, determine the velocity of for minimum cost and maximum production. So you have to find out both velocity value of using this formula as well as using this formula, minimum cost and maximum production. Okay, let's do that. And you need to get some data. Okay, let's use this data. Let's use this data to solve this problem. So I'm gonna grab this formula here, this formula for you. Okay, let's use this formula and fill in the blanks. Let's use this formula to complete this question. So what is C? C is that constant, the Taylor's constant, which is 175. And what is this is the cutting speed is in feet per minute and tool life is in minutes. Okay. What is RM? RM is nothing but LM, the labor rate plus the burden. PM is 115, means 1.15. In decimal, it is 1.15. You see? And what is the basic labor rate? It is $13 an hour. And this is in hour. So can you convert it into minutes? Because the two Taylor's tool life, this formula is in minutes. So how would you go? This is per hour, dollars per hour. 1 hour is equal to 60 minutes. So if you do the math, you get this much dollars. $0.466 per minute is the labor rate. You will use this value over here. And tool changing time. Time to change the tool is 2 minutes. So you will use 2 minutes here. And time to grind the tool. Time to grind the tool is how much time is 3 minutes. This is 3 minutes. And tool grinding time. So maybe this labor is different. It has a different rate. So tool grinding time is LG plus 1BG. LG is $10 an hour. and 1 plus burden is 120%, 1.2. But you have to convert it into minutes. If 1 hour has 60 minutes, right? So you can use this formula to find out RG. RG equal to 0.366 per minute. You will use this value of RG over here. And DG, there are about regrinds 15 edges, 15 regrinds per tool and 3.75. So I'm gonna write down 3.75 per 15. So per edge you are paying $0.25 to regrind this much edge. So you will use this value over here, this value over here. And Taylor's tool life has the index value n equals to 0.1, so you will use n 0.1. So let's plug it in. If you plug it in over here, you get 120 surface feet per minute. Okay, please verify. Open your calculators. Let me write down here VCM equals to 175 times RM raised to the power n, which is 0.1. 0.466. This is this one. Okay, then time to grind the tool is 3 minutes. 3 minutes. And RG is 0.366. Plus DG, which is 0.25. Powered 0.1. Okay. Do you get 120 surface feet per minute? Please confirm. If you get that value, then we can move forward. Let me grab this one here. So if you do the math, you get this answer. This is a cutting speed to maximize the saving. Okay. Now, if I ask you what is the formula for cutting speed to maximize the production rate, so you will use this form. So let's use this formula. Grab this formula here. Okay, let's plug it in. The values here for maximizing the production Taylor's tool life constant is 175, 1 over zero point 0.1 minus 1 in the big bracket times 2. Tool changing time is TC 2 minutes, whole raised to power zero point 0.1. If you do the math, this is 131 surface feet per minute. This is a little bit faster because it makes sense. You are creating more parts with a little bit faster speed. You see my point? So Taylor's tool life, one is used to save the money, but the other one is used, don't worry about saving money, let's make more parts. If you have more orders from the customers, demand is very high, I will use this model for turning, facing, all the production processes. Have you understood this question? Can you solve similar question in your quiz or test next week? Let's solve another question. Suppose now you are using a carbide insert with 8 edges. So now you have 8 edges that costs $2.5. So how will you solve this question? Let's grab this formula. Now the Taylor's tool life constant is 400. So this C is 400. RM is not changing. Oh, sorry, this is changing. This is a different question per minute. And TG is 0. Per edge tool grinding cost is 0.3125. RM is 0.466. And tool changing time is 0.75. The Taylor's tool life index is 0.2. If you solve for this, you get 283 surface feet per minute. It's very, very high as compared to the other tool, which was maybe a high speed steel, but this is a carbide insert, which is a little bit stronger than the high speed steel. And similarly, if you use the other formula for VTM, let's use this formula to maximize the production rate. Okay, can you do the math here? 400 divided by 1 over 0.2 minus 1. This is in small parentheses. Let me remove this big bracket here. Times the tool changing time, which is 0.75, whole to the power 0.2. Do you get 321 surface feet per minute? Yes? Yes. Please do the math. Let me know if you get this answer. Yes, one student says yes, he got this answer. So I'm glad that you have understood. Have you understood the comparison of two different tools? So let me show you the comparison in our slides. So which one do you prefer? High speed steel, you have the cutting speed of 120 versus 283. Carbide tip is very, very high speed. You see the largest speed over here? Will you use, if you have a lot of parts order waiting, you will not compromise on the customer satisfaction. That's what total quality management requires you, to satisfy the customer. Quality means satisfy. If you don't satisfy his demands, you will lose your reputation of your company, which we don't want. We want to keep the customers happy. That's our main objective. So you will give, reduce the lead time. If he orders you, I need this car maybe in 1 month, so you have to fulfill his the requirement. Otherwise, you will have a bad reputation or a lot of backlogs. But for that, you need to increase your facility. Again, the cost is increasing, but on the other hand, you have more revenues from the customer's purchase. You see, they pay first, and then they wait for the cars or other motorcycles or other machines. Now calculate the minimum cost for both previous cases. So the raw material cost minimum let me show you the minimum cost here. So the material cost per piece is 85 cents. Setup cost is 0.05 dollars, and the workpiece diameter is 2.5 inch, and the length of cut is 10 inches. So you have to reduce the cost. So for high speed steel, let me grab the slide here. So Taylor's two life equation. So I wrote down something earlier differently. Let me show you. This is the time to machine, the length divided by feet times the speed. So suppose this is equal to dimensions inches per revolution. Speed is inches per second. Is this correct? $183. Revolutions per minute is 183. How much is the feet? 0.008. Some of the data is not completely given here, but it is coming in the next slides. This is comparison of high speed steel versus the carbide steel. So let's see the high speed steel. For the carbide insert only the CM, CC and CG differ. There this when you go home do this math again for two different tools and check if you get some cost per piece. The main objective is how much cost you are paying when you're using the carbide tip versus the high speed uh, steel tip. So let me show you the final result here. $3.29 when you are using carbide tips and $5.14 per piece when you use high speed steel tip. So I will use the carbide tip in order to reduce the cost of the parts per parts. Okay, you can do the analysis. So now we can further see what can we do further analysis. Let's do one more analysis, then you will see more interesting picture. So the high speed steel has higher CM, the cost of machining, the lower CC, higher CG, tool changing cost, and tool grinding cost, and past. So this is more further more analysis has been done here. But you don't need to go into that detail. You just at least you should know what is the cutting speed for maximum production, cutting speed for minimum cost. At least you should know this relationship. Furthermore, is just for your uh, more knowledge, you can understand how it varies. One should minimize the cost per part rather than maximizing the production rate. So these slides you will study on your own. Now we have finished this topic of the tool life and the cost of machining. So the main topic is we covered in our lecture today is this one. So now